All right. Hello, everyone. Thanks for joining our webinar. We are very, very glad to have you here. It's an international audience as usual. So the AMozone webinars are typically well attended from all over the world. We have people from different continents, North America, Europe, and Asia, to be correct. Um, so very excited to have you here. We have people from very different backgrounds and very different activities. So we hope for a very lively discussion. So the topic of today is a continuation of the webinar series we have been hosting in the last couple of years, the AMozone webinar series. So our company AM team has developed this model, and it has been applied throughout the last couple of years at so many sites, and we will take it now to the next level. So this webinar is really on the application side of AMozone and how this model can revolutionize, or actually is revolutionizing, ozonation, advanced oxidation process, and advanced treatment design and operation. So again, welcome to our webinar. So let's start with the objectives of today. Of course, the context of this webinar is advanced treatments. We have a lot of emerging needs. We will zoom in a little bit on those in a couple of slides, or in the next couple of slides. And yeah, this is really the big context, because the relevance probably of this webinar today is more than, let's say, a decade ago or 20 years ago, due to several aspects, including digitalization. The objectives of today are that we hope to provide you with really valuable new insights that are of practical relevance for you. We hope to inspire you a little bit on emerging applications of models in this domain, and how these things really offer practical value for process assessment, process design, and smart operation. So the format will be a hybrid presentation mode. We will do slides, different presenters, and then we will also bring some live polls to you and live Q&A. So we will have an open Q&A session from time to time. So we really invite you to ask a lot of questions. If you do so, please use the Q&A window. When you go over your screen, you will see a Q&A window. So do not use the chat, but use the Q&A window for the questions, and we will answer them live from time to time. So we hope really to hear from you. At the end of the webinar, there will be a quick questionnaire popping up. So please share your feedback, as we are really interested in continuously improving our webinars. So we will, of course, introduce our webinar team as well in a couple of slides. So the webinar content, transcends challenges. This is very interesting to look at. Where are we going in different parts of the world with these technologies? We will introduce to you the model, where we came from, and what exactly is behind, and why are we doing this? And then, which is the most interesting part of this webinar, we will go to case studies on various applications of the model in various stages of the technology lifecycle, from planning over design to final operation. And then we will end with some conclusions. So here is our webinar team for today. So I am Wim Oudenaert. I am CEO and co-founder at the AM team. So I have the pleasure today of hosting you to be the moderator of this webinar. And then we have also our colleague, Roberta Muyo, who is attending. Roberta is a project manager and senior simulation engineer. She has, by the way, worked on numerous full-scale designs across the world in Asia, North America, Europe. So she's very much acquainted with this technology. And the same goes for Giacomo. Giacomo is technology lead within the AM team. So he is actually also responsible for many of the developments of AMozone. So really has worked a lot on the model itself as well. And we have also Peter, who's working behind the scenes here. Peter is our VP Sales and Solutions. So he is setting up a lot of the new projects at the global scale with customers. So again, on behalf of our whole team, I welcome you to this webinar. Let's first set the scene a little bit. Let's zoom out. So why are we together today? Why are we doing this webinar? Well, we have some unprecedented challenges in the water industry, not only the amount of challenges, but also the speed at which they come and go, and the speed at which we really have to get them solved. Never before this was the case. One of those aspects is climate change mitigation, reducing carbon footprint, but also the adaptation. So the impact on water sources, for example, in the drinking water industry. But if we look at the wastewater industry or the wastewater world, like we used to call it within AM team, we have continuously more stringent effluent requirements, including emerging contaminants. In Europe, we call them micropollutants. In the United States, we call them trace organics or CECs. But in fact, it's emerging chemicals, you know. And the very fact that we have to reuse more water, for example, for potable purposes, or the very fact that drinking water companies are shifting more and more towards more impaired water sources, for example, shifting from groundwater to surface water. Well, these things really, really come to the forefront. And in the end, these different continents, which you see on the screen right now, are really, really coming closer and closer together to each other. And this makes it specifically interesting. So our company tries to tackle a lot of those big challenges with computer models. So we are developing and applying really globally unique computer solutions, modeling solutions. We work with a lot of utilities. I think we have worked with over 40, close to 50 different utilities now in various parts of the world. But we also work with technology companies a lot, and also a lot with engineering firms. So we try to support projects across the globe, either directly with end users or either in project consortia using the power of models. We are, of course, also offer some operational solutions as digital twins, but we will come back to this in the webinar. All right. So the tools AM team is very well known for, and you will see them across the case examples, is on one hand, computational fluid dynamics. We are not only applying CFD to help designing and developing oxidation technologies or advanced treatment trains. We are literally applying these technologies or these models for every single treatment process you can think of. It is physical, chemical, biological, electrochemical even, so all of these things. On the other hand, we're also quite well known for kinetic modeling or process modeling. This means the application of biological conversions or chemical conversions. And when we talk about ozonation or advanced oxidation, chemical kinetics are the relevant pathways, let's say. So these are the equations we have to include. And this is why we have developed AMozone. AMozone is a set of, in the meantime, a huge set of mathematical equations that really describe the chemistry of oxidation in real water, wastewater, drinking water, or other processed waters. We also like to combine frameworks because we try to prioritize mechanistic models because we believe in the power of the white box and the fact that humans try to understand a lot. So these are models based on physics, chemistry, biology. But on the other hand, data-driven models also have a huge potential for application in the water industry. We are talking about statistical models, machine learning, artificial intelligence. So these are also very valuable tools, and the combination of them is very, very powerful, especially when it comes to digital twin applications in real time. So also on this, we will give an example later in the webinar. So we will start with the first poll just to know who is in the audience. So I will quickly launch a poll here in which water industry applications you are active in. So I will launch the poll. So normally you should see it on the screen right now. Is it mainly drinking water? Are you more working in reuse? Are you in municipal wastewater or more at the industry side? You can also vote for different domains if you would like to, because some people are working in more of them. So the votes are coming in. So all of you have answered. Okay. All of you, still people are coming in. Almost all of you have answered. Okay, I will end the poll in 3 seconds. All right, let's take a look at the results. So here we see the results. Most of you are working in municipal wastewater. Very interesting because this domain is really emerging. Look at the new urban wastewater directive in Europe. Look at what's happening in reuse in the US. So yeah, it makes sense. A lot of things are happening there. But still, you can see also a lot of drinking water people. Why? Because also there, the application of ozone and advanced oxidation is really still growing, even though it has been applied for over a century. And then we have some people working in reuse and industrial water. So thanks for sharing your thoughts on this. So let's continue. Quick intro into the AMozone model, not too long, because we have had a lot of webinars on this in the past. But AMozone, it's important that you understand a little bit the framework in order to understand the webinar. So in fact, it is a virtual representation of the real processes, okay? So how do we do that? We have compiled a whole bunch of chemical formulas and we have written them inside a model, which is called AMozone. AMozone does not only predict ozone chemistry, but also predicts advanced oxidation chemistry, including UV, peroxide, and combinations of those. So some of these equations you see on the slide at the right-hand side. So it has peroxide chemistry, it has the chemistry of pH, ammonia, all of these interactions in a real water matrix. Of course, once you have this, you can start virtually replicating treatment plants. And this is what we do across various applications of the technologies. So AMozone, throughout the years, we started developing this over a decade ago, in fact, and really commercializing it 6 years ago. But in the meantime, it has been applied at over 40 full-scale sites in 3 continents. So AMozone is really growing or emerging as a very important solution in this field, especially to design, to make technology selections, and to go to smart operation. We have implemented this model in the software Sumo, which is a very powerful simulation engine. So this is where we run the model code in, or we run the simulation code in CFD, the 3D computational fluid dynamics model. We will also give examples on those. So first application stage is technology selection and feasibility. The questions here are, okay, what is the technology we would like to apply? What will be the removal rates? What is the risk on byproduct formation? What would be approximate sizing costs of this technology? So this is all in the planning stage. And here we apply the model to conduct virtual piloting in combination or in reduction of real piloting. Then we go to the design stage where these models are used to properly design reactors or equipment. And then ultimately, when the plants are being built, we can recycle those models again to the operational stage as a digital twin. So in those circumstances, the model can predict in real time target contaminant removal, byproduct formation, ozone residuals, etc., etc. So all of these different application areas are very distinct, but we are trying to recycle the model throughout the various stages. Also, not everybody starts in the planning stage. We are also working on a lot of already existing plants. So the applications are quite wide. Final poll, before we go to the case examples. So in which application domain are you most active? So we'll look at the polls now. The application domain. Launch the poll. Okay, normally you should be able to see the poll. So if you look at those 3 stages, which one or ones are most interesting for you? Is technology development and commercialization. So this is more for technology vendor people. Are you working more on plant design, more for engineering people, or are you really in the operations and optimization? And this is more for the end users, let's say. Okay, so votes are coming in. I will end the poll in, let's say, 3 seconds. Most of you have voted. Okay, I'll end the poll and share the results. Here we are. So it's nicely balanced here. Many of you are working on technology development and commercialization. It makes sense because a lot of growth is in that area as well. A lot of emerging technologies still are coming, but also a lot of you are at the operational side. This means you are operating ozone plants and are looking into improving them or maybe redesigning them. And then we have a lot of design people as well. So thank you for sharing your outcomes. All right, so this brings us to the case studies, and we have selected quite a variety for you. We have selected a mixture of drinking water and wastewater case examples. So drinking water case examples will be indicated with this blue droplet. You will see them coming back, and the wastewater cases will be indicated with a brown droplet. But also we have also made a selection across the various stages because we will be talking about virtual piloting, about applications in design stage, and also digital twin applications. So we will try to mix all of those to give you the most complete answer. And as you can see, we have worked with many different parties on these case examples. So thank you for the collaborations again, and we will, of course, show these case examples in more detail. So this brings us to the first part on virtual piloting, and I will hand over the floor or the microphone to Giacomo. Giacomo, the floor is yours.
Thank you. Thank you. Hi, everyone. I'll present to you the first part here of the virtual piloting. First slide will talk about the how we apply virtual piloting, so the framework. So very quickly, we use real data coming from an installation, and typically we take an actual sample of that water with which we do a batch test, and we observe how ozone is depleted, and we calibrate with those data the AMozone model. Together with that, we do also calibration on bromate measurement and micropollutants removal to do full calibration of the AMozone. These tests include all these measurements, and we take care of that. So once the model is calibrated, then it opens up a tremendous set of possibilities to run unlimited set of scenarios. Looking at what is the micropollutants removal or the bromate formation using different injection strategies, different injection configurations or control strategies of the dose we are going to give to that water volume. And in the case we're going into, it's a secondary effluent treatment case. I will show you how we can answer some of the most burning questions at the virtual piloting stage. So in this case, the utility had to size the installation, size the generator, understand how much their effluent nitrites from the biological tank were affecting would affect the ozonation step, and how they could reduce dissolved oxygen at the outlet of the ozone installation, because then they have a denitrification step later on, for which the dissolved oxygen is not ideal. So all these questions are typical of a virtual piloting step. In here, you can see an ozonation curve. The line is on the top left. You have the line, which is the model, and which is going through the batch test results, showing the ozone depletion. And with the calibrated model, then we can represent on your right side the ozone residuals at every point of the installation from inlet to outlet for many different scenarios. In this case, without going into much detail, they wanted to in particular test the effect of pure oxygen and air as as the main carrier to produce ozone, and what effect would that have on bromate formation and micropollutants removal, but also on the dissolved oxygen in the effluent, right? So the first and important question is, how big should be my installation? And in this case, we could reduce sensibly the capital cost here and optimize the space requirement for the installation. The sizing, helping the designer to size the ozone reactor. Nonetheless, in this stage, you also size the generator capacity. And in this case, it was pretty important to take into account the nitrite effect. Nitrites coming from the biological treatment operation can consume a large amount of ozone. Typically, it's defined as 3.43 milligrams of ozone per milligram of nitrogen as of nitrite as nitrogen. So it's a very important part of the produced ozone that goes basically to waste. But nonetheless, we could run long dynamic simulations using their real data from the effluent sensors at the biological plant and compare. In this case, you're saying the comparison between the counter current and the co-current injection of ozone. So on in one strategy, you inject the ozone from the ozonated gas from the diffusers, and the liquid goes down in the counter current, whereas in current, both liquid and fluid go to the upwards in the same direction. So this allows a slightly better bromate control, and also to be able to reduce the dissolved oxygen at the effluent. Of course, in this virtual piloting stage, the assumption is of perfect mixing, which needs to be taken care of in the detailed design phase with the CFD AMozone. Now, the virtual piloting is particularly important to answer the bigger design questions, right? And it speeds up the decision making, so it saves time, and also a significant amount of costs that imply experimental work. Time saving is enormous, and that is those are the two most important points. But also safety, it's nonetheless one of the major concerns regarding the real piloting, the experimental work. And of course, very, very important is that virtual piloting allows unlimited testing freedom and measurements possibilities. So you can measure anything everywhere in your virtual pilot. So it is used to answer the bigger decisions at the bigger questions at the preliminary design stage, and to go faster towards a detailed design stage, in which we approach then a very detailed set of questions on the baffle designs and diffusers location using the CFD AMozone combination, which will be the main topic of the part 2 that now will be presented by Roberta. But first we have a Q&A if we have some questions, of course, and we can have a small break.
Thanks, Giacomo. Yeah, indeed. So also to the audience, now we for sure start inviting for a lot of questions. We when we go through these cases, so feel free to use the Q&A. Already a couple of questions came in, so maybe Giacomo, you can answer some of them. So, for example, one specific question we had is one of the biggest challenges in advanced treatment design is the water matrix. The water matrix is specific for each site. So how does the model take into account this specificity of the matrix? Which variables, for example, do you use as an input? And how do you calibrate that model then?
Yeah, Correct. That's a very good recurring questions in the different webinars. So it's something that it's important to specify. The model is input required for the simulations is typically UV absorbance at 254. That's the indication that we typically use for the organics description. We use DOC as a variable, an input variable, but also information regarding the inorganic carbon is also important, which is also acting as a scavenger. But mainly on the ozone consumption, like fingerprint of a particular water or secondary effluent is the organics composition, and that is what makes the water metrics unique, and unique its reaction with ozone. And what we have seen from the batch test, every water has a typical ozone decomposition profile. That's why we take that into account with the calibration step, and we use all these information to best represent the organic composition there. Yeah.
Okay. All right. Thank you, Giacomo. So also maybe I can add something on the previous slides. I will go back to it here. Our philosophy is, of course, not to put them really against each other, because piloting sometimes is even mandatory. For example, when you look at the US reuse requirements in California, people cannot avoid piloting. But we see, of course, a lot of cases where we can really accelerate the whole process. And we see some cases in Europe where we can also completely replace it. It really depends on the case at hand and on the goals. But one thing is sure, we can certainly extend the knowledge significantly if at least it is done in parallel, and also potentially reduce, all the efforts of real piloting to an utmost minimum. So it really, again, depends on the objective: reuse, final discharge, regen, and which stage you are in. Okay. So I just wanted to add this to make it very clear. Okay, so we have another question that came in, Giacomo, before you leave, and we give it to Roberta. So thank you for your question. It is, apparently the co-current option shows less bromate formation, Giacomo, and this is what we have indeed confirmed with the Dutch case. We will actually come back to that specific case. What about the ozone transfer efficiency in that case? Are you not worried? That's the question.
Yeah, that is one of the main concern. That's why it was not a usual design choice, or because there is the typical concern of having a low or reduced ozone transfer efficiency, so to have some remaining ozone in the off gas. But typically what we observe from the model and the experimental work is that, especially for secondary effluent treatment, where the ozone demand is very strong from at the liquid side, and the consumption is basically almost instantaneous, especially in the first injection chamber. In that case, there is no ozone to be expected in the off gas. That makes the driving force from the gas to the liquid very strong toward through the whole height of the to the water depth.
Yeah. All right. Yeah, thank you. So indeed, this is a promising concept, and probably there's still some work to be done in, tailoring the process to secondary effluents, compared to drinking water, because in many cases now, wastewater installations, let's say, are designed or using rules of thumb from drinking water fields, while actually the matrix is quite different, and that's what you are referring to here. You really have an absorption power from the gas phase to the liquid phase in addition. All right, good. We have a couple of other questions. We will come back to them later. But first, we will give it to Roberta. So Roberta, the floor is yours. You can bring us to the world of design.
Yes, all right. Thanks, Wim. So indeed, we step into part 2 which is the second application of the AMozone model. So after the feasibility study with the virtual piloting, we can apply AMozone in the detailed design stage. And we do this by combining the CFD, so the computational fluid dynamic, the physics, with the chemistry, so the mechanistic model AMozone. By combining these two models, we can actually look into optimizing the design in terms of mixing, for example, by having a plug flow distribution in the ozone contactor, or we can focus on the kinetics and maximizing the transfer efficiency, minimizing the capital cost. Another ozone CFD AMozone application is the minimizing the byproducts formation. So in this case, the bromate concentration. And a final application of the CFD AMozone combination is to find the optimal location of the injection of chemicals. For example, when it comes to bromate suppression strategy, we can simulate the addition of peroxide, and the question is where to optimally place it to have an even distribution of the chemicals in the reactor. So this is a bit the framework of the CFD combination of CFD and AMozone for the design stage. And here the first case example, it's a drinking water application in Canada, and where we work with our customer AMozone, which was in charge of renovating the ozone installation, the pre-ozonation contactor. So it was a design retrofit question. And in that case, the main challenge was to deal with an existing design, which has some physical constraint. For example, it was difficult to place the side stream injection pipe there. So there were some space limitation. And the goal they had to maximize the mass transfer efficiency of ozone, which means also enhancing the mixing between the side stream injection and the mainstream flow. So in this figure here, with these streamlines that you see, here we can compare two design configuration of the side stream injection pipe. First one, we started with a more simple configuration with one nozzle at the end of the side stream pipe. And there we saw that there was a strong shortcut of the side stream water into the ozone contactor, flowing along the walls just straight to the outlet, which means that the mixing, the contact of the ozonated water with the mainstream flow was not optimal. So then we tested a 3-nozzle configuration approach that was able to dissipate a bit of energy, so reduce the velocity, especially in the first chamber, leading to better mixing of the side stream flow with the mainstream flow. So this was a specific design optimization question, and now here on the left you can see a volume rendering of the dissolved ozone concentration in the pre-ozonation contactor in the two configurations, so 1 nozzle and the 3-nozzle configuration. And you basically can see that with the 3-nozzle configuration, locally the dissolved ozone is higher in the first chamber, which means that also the transfer efficiency is more optimal in that region with the 3 nozzles. So once we define the optimized design that meets the standard in the design criteria, then we can further optimizing and fine-tune the operation. So optimize the operation, and in this case, what we did was to test different side stream injection flow to verify that the mass transfer efficiency was maintained. And that's what we could verify with the model. Mass transfer efficiency was kept very, very high despite the lower side stream injection flow. So that was a drinking water application, design retrofit. Now the one that we present in this slide is it's a secondary effluent application for the removal of micropollutants and minimum bromate formation. And this is an example of a full-scale ozonation plant design where the AMozone model was used even from the virtual piloting stage, starting 4 years ago now. To the detailed design stage. So in this case, we could test with the CFD AMozone model. We could test different design configuration, and in the end, together with the BAU team and the water utility, the DOM, we decided to go for a co-current configuration, which is, let's say, less usual for an ozonation contactor, because this configuration lead to better and uniform ozone contact with the water, and this allow for same micropollutants removal with lower bromate formation, around 30% bromate formation. So this is an example where the CFD AMozone could be used to for the detailed design of a full-scale ozonation plant that is not existing. And in this particular case, we could test several design configuration by changing, for example, number of diffusers, testing the addition of peroxide to lower the bromate, different buffer configuration. So all kinds of degrees of freedom we could take into account in a matter of weeks, and we could address the key variables for the water utility, so the bromate formation and the micropollutants removal. So here, for example, is benzotriazone removal and venlafaxine. So a lot here is possible, and this is a very interesting case to us, because it started from the virtual piloting, then we completed the part 2, so the design stage, and this is now proceeding to the third part of the AMozone application, which is the digital twin that my colleague Giacomo will present.
All right, thank you, Roberta. So Giacomo, before we dig into the digital twins, and Roberta, we have a couple of more questions that came in. So it's a very good discussion ongoing. So, for example, one question is very relevant in view of the urban wastewater treatment directive. So some specific micropollutants are being mentioned in that regulation, or Switzerland has specific components, the Netherlands has specific components. Can you elaborate a little bit more on which micropollutants or which trace organics are included or can be included in the model? So maybe Roberta, you can say something about this.
Yeah, so indeed, so AMozone is, again, it's a mechanistic model. So it's a set of chemical equation, which means that we right now we have more than 100 micropollutants or contaminants of emerging concern included in our database. And we basically can include as many as we want, as long as we have on the literature the rate constant, so the sensitivity to ozone and radicals. So actually, whatever compound can be included with even without specific literature. If experimental studies are present, are available, then we can use them and include those micropollutants.
All right. Yeah, we also had a similar question on PFAS. Like, is it being removed or not by ozone? Yeah, what about this, Roberta?
Well, based on our experience, ozonation is not that efficient with PFAS removal. What we normally observe is that the combination of ozone and granular activated carbon in that case can be really the key solution in for this specific compounds.
Yeah. All right. Yeah, and with regard to PFAS, of course, our team is currently working on a model for adsorption on activated carbon. We will say something about this at the end of the webinar, so to also be able to answer the many questions actually we have on that aspect as well. So we have another question. Let me see. So yes, about model validation. Can you say something about that, Roberta? Have we how we tackled that in the past, and how we typically cope with that?
Yes, so indeed we can. So first of all, what we normally do, we calibrate the model with pilot experimental data if these are available, or we do dedicated batch experiments with an accredited lab where we can really calibrate the model, so giving the fingerprint of the water. So once the model is then calibrated, of course, if it's an existing design where we optimize the design configuration, for example, and there is some data available, we can also compare the model performance with the real plant data and validate the model. In case it's a new design, yeah, there are no data, so the only possibility then is to wait until the installation is operational, and then we can verify these aspects.
Yeah. All right. Thanks, Roberta. Great. Yeah, maybe good to mention is also that we have one of our customers in the US that was testing the co-current versus counter-current in their lab pilot facilities, because they have a lot of testing facilities. And yeah, these results were quite confirmed as well there. Like slightly higher micropollutant removal, but lower bromate formation in an effluent matrix. So these things, of course, working with a lot of parties as well, next to looking at data, is very important to keep the work ongoing. All right, Roberta, thank you. So we will go back to Giacomo, because he will now go to the last stage, let's say, of the models, which is the real-time or the most advanced application, digital twins. So Giacomo, you can tell a bit more about this here.
All right, thank you. All right, so the digital twins are like representation of a real installation, but they're very detailed representation. So how we design a digital twin is to as starting from the CFD information, so hydraulics and chemistry, and take that information on recycle flows, on hotspots for chemical reactions into a CFD informed tool. That's how we call the digital twin, or the dynamic tool, right? A model that runs faster, it's informed by the CFD exercise, and it can run several days of simulation. And in this case, at the bottom of the screen, you see simulations around bromate formation or micropollutants removal as a result of different operating conditions or operating strategies, right? Or injection strategies. This information at this point can be used to train the operators, the staff operating the system, or can be sent to the control room where a better decision making can be made, like how to do the next control actions, how to operate the system, or if maintenance is going on. So if I have to shut down a generator, what would happen to the other reactors? Or if I have to convey all the flow to one reactor, how should I behave best, right? Apart from the fact of the everyday operation, which can be also automated with the supervision of the operators, right? So that's the principle of the digital twin. So in this case, we're bringing here to the surface a nice exercise we're doing with PWN, a drinking water facility in the Netherlands. They have high ambitions for getting to net zero. They have a very big digitalization program ongoing, and they strive for the highest quality standard of their water production. Now, with them, we created the digital twin of their UV peroxide installation using AMozone, with which they can do sensoring scenario analysis. They can optimize the UV dose, run scenarios depending on variability of influent characteristics, and also even plan the operation based on their carbon footprint, right? So we calibrated and validated the model with their experimental data. So they have measurements, they have sensors on site, and we could run several simulations of what happens what happened in the past, comparing with their data, and then run simulations for the future. One example that we bring up here is regarding, beside the effluent quality, which we also look at very closely. Here, they were interested in operational scenarios in terms of carbon emissions. What would be the scenario leading to lower carbon emission? Here we see a few days zoomed in, right, in which during the night, of course, we use the whole power from the grid, whereas during the day, they could make use of solar panels, so their carbon emissions go down, right? Apart from some cloudy days, which are, can be frequent in the Netherlands, in which still some power from the grid needs to be used, right? So using a little bit of additional peroxide, for instance, to reduce the dose of the UV light from the UV lamps helps in reducing the power. Of course, you cannot reduce that too much, but it gives you the chance to lower your carbon emissions to some extent. And you can also test different operational strategies depending on influent variabilities, like a decrease in DOC that might be expected in the future. So beside this, we also looked at the effluent quality, but we'll keep this for another webinar. Now we have a question for you. What is or are the primary concerns for the plants you are involved in? And well, is it byproduct minimization? Is it target contaminant removal performance? Is it disinfection, or is it cost optimization? Very curious. Let's give a little bit of time to select the most appropriate one or ones of your primary concerns, and maybe in 3 seconds we can look at the results. All right, the primary concern for many is target contaminant removal. So that's we could see this coming, and of course byproduct mitigation, especially in this case, depending on the UV dose or the ozone dose. It's very important to take care of like bromate or byproducts from the breakdown of some of the chemicals. Cost optimization is at the same importance, but also disinfection. There is a good percentage there for which is a concern. All right, thank you very much for this information, and then we can have another small Q&A before concluding. Yeah.
Yes, Giacomo. So one more technical question. So the chemical conversions of this, because we have shown literally bromate formation in 3D. We have shown the removal of target contaminants in 3D, which is quite unprecedented. It's only possible with these tools. How do we do that? Like, how is the chemical model literally integrated into the CFD model? That was a question we got.
Oh, okay. Yeah. Indeed. So now the AMozone is pretty extended, and we are extending that in both on the let's say on the Sumo platform that we use for running it, and so for the dynamic modeling, but also in the CFD at the same time. So the CFD AMozone coupling contains all the reactions we've been talking about. So these are reactions with nitrogen species, with inorganic carbon, with the organics, and all the micropollutants that can be integrated, as also Roberta mentioned. So yeah.
All right. Thank you, Giacomo. Yes. All right. Yeah, maybe interesting to add is there that if you don't look at those results, it's hard to understand how local conditions drive, for example, bromate formation. Typically, people refer to, okay, I get this bromate when I dose this amount of ozone, but in fact, what is really correct is that I get this bromate if I get these local ozone concentrations, and this is of course another paradigm that we can actually integrate into the next level of designs. Just talking about bromate, but we can talk about a lot of other variables as well.
Yeah.
Okay.
Yeah, totally. Yeah.
All right, so thanks, Giacomo. We will, for the audience, feel free to ask some more questions in the Q&A, because now we will go towards the conclusions end of this presentation, but we will still have some time to answer some more questions at the end. So feel free to drop them in the Q&A window. So this brings us to some practical aspects, because you might be wondering, okay, how do we now use this? It looks all fancy, but now how do we use these applications in these various stages? Well, let's talk about some practicalities. What we see in all of these projects is that the data we need to execute such projects is very limited. We typically get started with whatever data is already existing. Typically, this is about the plant layout, operational settings, and basic quality, water quality information. For example, pH, DOC, ammonia. So more of the basic variables. And this is where we typically get very far with. And of course, in addition, we use piloting data if available. And of course, in addition, we use some batch testing as well. But we typically work in different parts of the world without on-site work or very limited on-site work, which is also very important. And the timing, as my colleagues have in several case examples mentioned, is quite fast, it's quite short. So first results are available within weeks. And we do nowadays quite big projects, quite big really design projects in a matter of weeks or months. So this shows you a little bit the practicality of where we come from, because 10 years ago, 15 years ago, this would have not been possible. How we work together with different parties in the market, it's in various ways. It really depends on the setup. Either we are directly contracted by utilities or end users, or we are part of a very big consortia of projects. So, but typically it's in collaborative efforts with equipment parties, engineering companies, and the end users. This gives really the most of the value, looking at those things together and iterating along the way. So some important aspects to consider. This brings us to the conclusions of this webinar. Well, ozone exists for over a century. I think it was 1905 or 10, around that period. So already quite a while, and it's more important than ever. It's more emerging than ever. Simply look at reuse. Simply look at the emerging regulation in the urban wastewater directive. So yeah, it's becoming more and more important. What are the challenges that are standing in the way of implementing such technologies? It is the unicity of the water matrix. It is the very fact that you have to do some piloting and trialing, typically, if you don't have good models at hand. And it is the balancing act of a design, OPEX, CAPEX, byproducts, size, the footprint, carbon, even the embedded carbon in your structure. So it's becoming more and more complex. And when you look at the operation, it is all about acceleration of the training of staff that will have to operate that plant, or on smartly operating and controlling that plant. So the model is now in the market for 5 to 6 years. We have been involved in over 40 full-scale facilities. And all we can say is that the feedback is really, really very positive. And yeah, we expect that the growth will continue and even accelerate in the months and years to come of this solution. What is very important for many of you likely is that we are working on extensions, because typically it is not a standalone process. Typically, these processes are part of a whole treatment train. So we are working, for example, on combinations with activated carbon, including PFAS, so components that are hard to remove with oxidation technologies, biological, granular, powdered activated carbon, but also other unit operations of treatment, of advanced treatments. So this might be very interesting for you to know, because yeah, likely in the following webinars, we will also be talking about these applications. This webinar was mainly on the application side. We didn't really go very in depth on the science or the technicalities, but we have done this in the previous webinars. So if you really want some more fundamental aspects, for example, on bromate chemistry, what is the impact of my matrix on operation, on design, you can certainly revisit our YouTube channel. You see the link on the screen here, where we have so many full recordings and snippets shared with you for you. Okay, so feel free to for the diehard fans of these technologies, feel free to visit our YouTube channel. So for the people that have to leave right now, don't forget to fill in the questionnaire. And of course, you can always reach us at this email address. And I also want to thank you for joining our webinar. Yeah, it's always nice to have you so long with us. It's 1 hour of full content. And for the people that still want to stay, we certainly have some more space for Q&A. So I will check the Q&A, the questions and answers, and then we can still spend some time on some questions. Okay, there was a question. Okay, what do you mean by saying that ozonation in the next 100 years is more emerging? What I meant is the technology exists for over 100 years, and it is more emerging than ever. Okay, it just gets other applications than in the past. When the technology really started, it was really for drinking water applications. So, but now we see the growth in the reuse and in the micropollutant removal, of course. Okay, another question I have is on the design. So maybe Giacomo, that's a question for you. Can the model simulate different technologies? For example, bubble diffusion, comparing that with side stream injection, or maybe other technologies. Can the model be used to compare and benchmark those technologies?
Yeah, sure. That's something we did very quite often, I would say. So comparing different nozzles geometry for injection. So looking really at the details in CFD of how the gas is injected in the liquid and how it behaves. So locally, how the mixing happens and the reaction in front of the nozzles are happening, but also comparing nozzles injection or side stream nozzles injection with fine bubble diffusers in co-current or counter-current. And especially it's very interesting to see this performing in CFD, where you can optimize nozzles direction, depth, and penetration into the reactor to optimize the contact time and the efficacy of the ozone injection.
And what about the combination of various oxidation technologies, mixtures of AOPs, for example?
Oh yeah. The combination, it's now more and more frequent that we create combined models of ozone and UV systems, UV peroxide, UV chlorine systems as well, because there are many questions coming up on the alternation or different combinations of what is the effect of the different combinations of this technology. In particular, we mentioned the work on activated carbon we are doing. It is particularly interesting to combine in different modes activated carbon and ozonation to minimize the ozone dosage, but also minimize the cost of activated carbon renewal. There is the possibility to even, it seems possible to chemically reduce bromate with biologically activated carbon. So activated carbon having a biofilm on top, which does a kind of reduction effect on the formed bromate from the ozone installation. So these are the things that are even coming further in the next combinations. But yeah, all the AOPs can be combined in many different ways.
Yeah. All right. And related to that, we have another question. So oxidation technologies or adsorption is just one option of advanced treatments. Another very big segment, let's say, of technology is membranes. One question here is on the application of such models to do virtual piloting of membrane systems, for example, ultrafiltration. What is your take on this, Giacomo?
Oh, that's very interesting. Yeah. Yeah, so combine ultrafiltration combined with ozonation, you mean? Right? That
No,
was
like as a standalone, or maybe a combination.
Okay, yeah. So that's something that can be already included in the process configuration. Yeah, I was thinking more in terms of fouling minimization using ozone there, but we're pushing a little bit too far. But yeah, that's something that can already be done, having a membrane filtration and then combinations of AOPs. Yeah.
Okay. All right. That well, maybe leaves us to one good question. Are you coming over to Finland? Well, well, here's the good news. We are working in 22 different countries, including Finland. So so you can certainly work with us. We can certainly work together. So I think we have to stop here. Thanks, Giacomo. Thanks, Roberta, for presenting and answering these questions. And again, thanks the audience for being here again. We have formed a really nice audience and community around AMozone. So we hope to welcome you in one of our next webinars and maybe work together one day. So again, don't forget to fill in the questionnaire, and thanks again for attending. So it was really a pleasure to have you. Thank you very much.